Everything we do in chemistry is devoted to trying to understand things at the atomic level. And so in this next little movie, I'm going to try to introduce you very superficially to how kinetic studies can help us understand what's going on with reactions at that atomic and molecular level. So let's start off by considering a nice simple substitution reaction, a single displacement reaction, however you want to put it. X starts off bonded to A and ends up bonded to B. Now let's think about how this reaction could take place. Well, the first thing that's got to happen is that A's got to start breaking the bond to X. Okay, and then as that bond breaks, B swoops in and grabs X. So that relies on two things. The first is you've got to be able to break that AX bond, and you have to have enough energy for that, and so you've got to have a collision of AX, maybe with the wall of the container, maybe with another molecule, and that collision has to have the right energy. At the superficial level, that collision has to have the activation energy in order for that bond to start breaking. But even if that bond does start breaking, if there's nothing else around, well, X is just going to come back to A as if nothing had happened. So therefore, it's not enough that AX has a collision with the right enough energy to start breaking that bond, but there has to be a molecule of B in the right place at the right time. Okay, now that's trying to understand what's happening at that atomic and molecular level just by applying common sense, right? If B is going to grab X away from A, well then first of all A's got to start losing X, and B has got to be in the right place at the right time. Now, let's think about what that means associated with what we have been thinking about up till now. What would happen if we doubled the concentration of AX? Well, that would mean that we'll double the number of appropriate collisions. If there's twice as many molecules of AX moving around and they're bumping into things, if you've got twice as many of them, well, then you're going to have twice as many collisions, and you're going to have the same proportion of those collisions that have the right energy, so you'll have twice as many collisions with the right energy, and so that will double the rate. So in other words, we can say, because the reaction first of all relies upon AX having the right collision, the rate must be proportional to the concentration of AX. Now how about if we were to triple the concentration of B? Well, remember, the reaction also relies upon there being a B in the right place at the right time. And so if we triple the concentration of B, we're going to triple the chances that there's a B in the right place at the right time. And if we triple the chances of B being in the right place at the right time, we'll triple the number of possible reactions, or in other words, we will triple the rate. And thus we can say the rate is proportional to the concentration of B. Because we are saying that our reaction relies upon, first of all, an AX colliding with the right energy, and then B being in the right place at the right time, we can say overall that the rate is proportional to the concentration of AX, the number of AX molecules, and it's also proportional to the concentration of B, the number of B's ready to be in the right place at the right time. Putting that all together, doubling AX and tripling B would double the rate and then triple the rate, so the rate goes up by 6. And of course, putting all that together, we can come up with the rate law that would correspond to this atomic level explanation of the reaction. The rate is K, that little constant that relies upon many, many things, times the concentration of AX times the concentration of B. Okay, if we see a nice simple reaction where the observed rate law, because remember this is observed, is K times AX times B, well then we can say, well, there's got to be an AX and there's got to be a B involved somewhere in the reaction determining that rate. Let's take that same idea and think about how can we get a second order reaction in one species. This is a second order reaction in two species, being first order in each. But how would we get a second order reaction in one species? Well, consider that reaction. A plus A, one collides, and one is in the right place at the right time. So if we double the concentration of A, well then we would double the number of appropriate collisions, and so we would double the rate. Then of course if we double the concentration of A, we're also doubling the chances that there is an A being in the right place at the right time, and so that in itself would double the rate. So by doubling the concentration of A, we double the number of reactions, and we double the chances that A is in the right place at the right time. So we double the rate goes up by 4. This would be a case in which the rate is equal to K times the concentration of A squared, because you're doubling the A's that can have the collisions, which I've expressed in this sort of blue color here, and you are doubling the number of A's that can be in the right place at the right time, expressed in this purple. Obviously the A's are the same, but when you double the amount of A, you have the effect of doubling that and doubling that.